In this lesson, we will be looking at some different exponential growth and decay word problems. So here's a little um, joke to get you started. So if you want to hit pause and read it, go ahead. All right, here are some examples of some growth and decay kinds of problems. So here's an equation right here um, that if you look at the graph for this situation, you can see it's going down and to the right. So you can see it's a decay equation. Um, this right up here is the standard equation that you will use for growth and decay problems. What I want you to notice in this case is that your R, or your ratio, is 0.5. When we're dealing with decay kinds of problems, that R number needs to be somewhere between 0 and 1. It can't be 0, it can't be 1, but it can be anything in between in order for it to be a decay kind of a situation. Okay? Over here, you can see that your ratio is 2. In order for it to be a growth equation, and you can see by the graph that it's going up and to the right, in order for it to be a growth equation, your ratio has to be bigger than 1. Notice your R can never be exactly 1, and here's why your R can't be exactly 1. If we take, for instance, this situation right here, y equals 3 times 1 to the x, it doesn't matter what we put in for x, because when we take 1 to the 1 times 3, we get 3. When we take 1 squared times 3, we get 3. When we take 1 to the third times 3, we get 3. Nothing is growing, nothing is changing, it's not decaying, and so it doesn't create a growth or decay situation when your ratio is 1. Similarly, when your ratio is a negative number, so we look at the equation 3 times negative 2 to the x. When we do that, then when we type in, when x is 1, 3 times negative 2 to the 1 is negative 6. 3 times negative 2 squared, so I have to take negative 2 squared first, which is 4, times 3 is positive 12. Negative 2 cubed is negative 8, times 3 is negative 24, okay? And what happens if you look at what's happening with the dots on the graph is they jump back and forth, back and forth, back and forth. It's not consistently growing, it's not consistently decaying, it's just kind of a mess. So growth and decay problems have to have this. If it's a growth situation, your R right here has to be a number that's bigger than 1. And if it's a decay situation, your R has to be a number that's between 0 and 1. Either way, whether you're growing or decaying, R always stands for the amount of people or substance or money or whatever that you get to retain each time. Okay, so if something is growing, let's say you start with 50 grams of a substance of bacteria, let's say, and that bacteria is going to grow, and it's going to grow by 3% an hour. Well, you need to multiply it by 1.03 because the 1 will give you the 100% of what you had back again. So the 1 will give you the 50 grams that you started with back again, and then the 0.03 will add on to that 1 and it'll grow by 3%. Okay? If it was decaying by 3%, that doesn't mean you want to multiply it by 0.03. That means you want to multiply it by 0.97 because it's always what you get to retain is what the R should be. Retain means what you get to keep. So if you're losing 3%, that's great, but you're still keeping 97%. Okay? So, and that'll make more sense, I think, as we do some story problems. Okay? So here's our first situation. It's talking about cell phones, and I know that's an archaic picture of a cell phone. Maybe that was what your first cell phone looked like. In 1985, there was 285 cell phone subscribers in the town of Centerville. The number increased by 75% each year. So increase is a big word there. That means it's growing, obviously. How many cell phone subscribers were there in Centerville in the year 1994? Okay, we know that this is a growth equation, and we know then that our ratio has to be bigger than 1. I always kind of like to think of this too. What you end with, this is another way to write this, is what you start with times 1 plus or minus your percent, we'll talk about that, to the time. Okay, some people like to think about it like that, and that's one way to do it. Okay, in this case, I started with 285 cell phone subscribers. I am growing by 75%, so that means I need to take that 75% and add it to 1. Again, the 1 is going to give me the 285 subscribers back again because I'm going to multiply that. That's 100% of what I had plus 75%, so plus 0.75, and 1 plus 0.75 would be 1.75. Okay, time we need to talk about. We're going from the year 1985 until the year 1994, which is 9 years. Okay, and then I will just simply plug that into my calculator, and I should come out to get about, I'm going to change this to about, 43,872 people. Okay, so that's about what should happen. All right, in the next one, the population again is increasing at a rate of 3% a year. It continues to grow. It starts at 1 million. Okay, so it starts at 1 million people. The starting amount is that A, that initial amount. So it starts at 1 million people. And you'll figure out some shortcuts to this as we go along. It's growing by 3%, so I need the 1 there to get my 1 million people back again, plus a 0.03 for that additional 3% that it's growing. Notice your percentage does get written as a decimal, so you do need to move the decimal 2 places to the left. In this case, I'm needing to know my time. I don't know it, but I know that at the end of what I'm trying to figure out, I need the population to have doubled. So I need the population when it started at 1 million. If it doubled, then it would end at 2 million. Okay? And so then, in order to solve for t, I will divide by 1 million. Whoops. And of course, I get 2 equals 1.03 to the t. And that's kind of your shortcut. When you're doubling, you're going to end up with twice of whatever you had. And it doesn't really matter what you start with. That's going to end up over there as a 2. If I said you're going to triple it, it would be a 3 on the left side. Okay? But that's what it's going to look like. And then you need to solve this, and you cannot get 2 and 1.03 as powers of the same number. So the only choice you have to solve this is to take the log of both sides. So that's what I will do. When I use my log properties then, this t needs to come out in front. And so then I will have the log of 2 equals t times the log of 1.03. And then to solve for t, I will divide by log of 1.03. That drops. And I will stick this into my calculator. Make sure you close your parentheses after you've typed in log 2. And you should get about 23.5 or 45 years. Okay, when you type that into your calculator. Okay, make sure you look at your units. It did say up here that time was measured in years, so be careful about that. All right, this one's a tricky one, okay? So bear with me when we do this one. We got it, but it will be a little bit tricky, okay? So in the year 2000, Nigeria had an estimated population of 127 million. The United States had a population of 278 million. Nigeria's population will grow 2.6 each year, and the United States' will grow 0.9% each year. The question is, when will Nigeria's population be more than that of the United States? So I'm going to kind of think about this. The question is, when will Nigeria be bigger than the United States? Okay, so I'm going to kind of think about making a population model for Nigeria. And again, Nigeria starts at 127 million. I'm not going to put all the zeros in because the zeros will end up canceling each other out anyways, so it doesn't really matter. So I'm going to put 127 million, since they're both in millions. If both populations were not in millions, I could not cancel those zeros out. But since they are, I can do that. Okay? So Nigeria is 127 million. It is growing by 2.6% each year. So again, I need the 1 for the 100% back again, plus the 0.026 for 2.6% more. I don't know my time. That's what I'm needing to figure out in this case. And then the United States starts at 278 million, but it grows by 1.009. Again, 0.9%, if you move the decimal 2 places to the left, would be 0.009 to the t. Okay? Now, I have to solve for t, and that is not going to be too terribly fun here. Obviously, I cannot get these as powers of the same number, so what I need to do is I need to take the log of both sides. Okay, so that's what I'm going to start out by doing first. Then what I want to realize is that I have really a multiplication symbol in here. And so what I can do then is I can use my log properties that say if I'm multiplying two quantities, this one and this one, I can separate them into two different logs and add them. Okay, so that's what I'm doing there. And then of course I'll do that same thing on the other side. I have a multiplication symbol here. I can use my log properties and I can make this be log of 278 plus log of 1.009 to the t. Okay, I don't know why this is here. I'm going to move it. All right, so that helped me just a little bit, but not a ton. Okay, now I'm going to use the log property that says the exponent can come out front, and I'm going to do that both places. Okay, so I will have the log of 127 plus t times the log of 1.026 will be greater than the log of 278 plus t times the log of 1.009. All right, still some variables in here. I've got these t's, which is not helping me very much. At this point, what I want to do is I want to get a number for this. So a gross icky decimal that I can do that with. And I also want to get a number for this. Okay, so I will leave this as log of 127 for right now, just so that I don't have so many icky decimals to work with. Then I'm going to type into my calculator log of 1.026. And when I do that, I will get about 0.01147. And then, of course, you have your t right there. Okay? Greater than log of 278 plus, and then I'm going to type in log of 1.009 into my calculator. Again, I'll get a gross icky decimal, and it'll be about 0.003891, and then of course you have your t right there. Okay, now I know these are icky numbers, but we can deal with them. So what I want to do is I want to get all the, or combine the t's, so I will subtract this quantity right here. Okay, and when I do that, I will end up with log of 127 plus 0.007256t is greater than log of 278. Okay, I'm getting there. My goal again is to get t by itself. So I want to subtract log of 27, or log of 127. Okay, so I can make this 0.007256t is greater than log of 278 minus log of 127. Now, if I wanted to, I could put those two together on the right-hand side as one log of 278 over 127. So if you want to do that, that's totally fine. In fact, I will do that just so that we can practice our log properties. But remember, we have a log property that says if you're subtracting two logs, you can make them be one log. And I can make that be 278 over 127, like that. Okay? And then obviously to solve for t, I will divide by this gross number here. And t should come out to be somewhere to be about 46.9 years, greater than about 46.9 years, or we'll just round that off to the nearest number and say 47 years. And if you went all the way back up to the beginning, we started in the year 2000. And so when we started in the year 2000 and we went 47 years later, that will be in the year 2047. Okay, so that was a tricky one. All right, these are a little shorter now, not so complicated. HTI bought a computer for $2,500. It is expected to depreciate. That means to go down 20% each year. What will the value of the computer be in 2 years? Okay. So again, I like to think of it like this. What you end with is what you start with times 1, either plus or minus the ratio. This is the same thing to the t. You guys know it as this formula. Either way, it's fine. But the computer's initial investment was $2,500. Now, this is where it gets tricky, okay? So it's going to depreciate 20%. That doesn't mean that I'm going to put 0.2 right here. Because again, what goes in the parentheses, what that R is in this formula right here, is always what you get to retain. So if you're losing 20%, that means it gets to keep 80% of the computer's value. Or you can do 1 minus 0.2 right there. Either way is fine. And then, of course, I have to figure out time, which would be 2 years in this case. And when I type that into my calculator, I should get about $1,600. All right. Similarly, a cup of coffee contains 130 milligrams of caffeine. It is eliminated from the body at 11% per hour. How long will it take for 90% of this caffeine to be eliminated from a person's body? All right, again, this is what you're ending with. This is what you're starting with. Okay? Clearly, I'm starting with 130 milligrams, so I can do that. I've got 2 different percentages here, so be careful. This is what I'm ending with, and what I'm ending with over here is I'm ending with 90% of 130 milligrams. And if I take 90% of 130 milligrams, or no, sorry. The question is, how long will it take for 90% of this caffeine to be eliminated from a person's body? Okay, so if 90% of it is eliminated, okay, we'll go like this. 90% of 130 is 117 milligrams. So basically what it's saying, though, you got to be really careful, is 117 milligrams are going to be gone. But this value right here is always what you end with. And I'm not ending with 117 milligrams. I want 117 milligrams of those 130 to be gone. So that means I have 13 milligrams of the 130 left. Okay? So 117 are gone and 13 will be left. And then your ratio, of course, you're losing 11% of the caffeine each hour. However, it's not what you lose, it's what you retain. So if you're losing 11%, you retain 89% of the caffeine each hour. And then, of course, you don't know the time. All right, the trickiest part is getting the equation set up right, and then I think you'll be okay. I want to divide by 130. And so 13 divided by 130, of course, is 1/10. And I can't get 1/10 and 0.89 as powers of the same number, so I will take the log of both sides. And I will also remember that this t then can come out in front. So I will have the log of 1/10 equals t times the log of 0.89. And then, of course, to divide, or to solve for t, I will divide by log of 0.89. And then you will put that into your calculator, and t will come out to be about 19.76 hours in this case. Your time is in hours in this case. All right. Last one. Right out of college, you buy a condominium for $85,000. You plan to buy a house in 5 years. If the condo appreciates at 5% a year, what will the value be worth when you sell it to buy your home? And if it depreciates at 3% a year, what will it be worth? Okay, so let's first of all figure out if it appreciates. Then what will happen is it started at $85,000. It's growing by 5%, so you need the 1 so that you get 100% back of what you started with plus 5% more. And then that's happening for 5 years. And when you do that, it gets to be about $108,483.93. So you've made a little bit of money on that condominium in 5 years. If it were to depreciate or to go down, sorry, I spelled that all wrong, then you would start at $85,000. It's depreciating 3%, and again, it's not what you lose, it's what you get to retain. So if you're losing 3%, you get to keep 97% of what you had, and then to the fifth power. And when you type that into your calculator, you'll get $72,992.39. So that's how each of those would look. All right, that'll do it.